Hello students, today you are going to learn about prism. Prism, it is a transparent material bound by two plane surfaces inclined to each other at an angle. We call it as the angle of the prism. These are the two plane surfaces A, B, C, D and A, B, E, F. These are the two plane surfaces. They are inclined to each other, forming an angle. This angle is called the angle of the prism. This part, the rectangular part DCEF, is called the base of the prism. This is one of the optical instruments that you are learning in this chapter, chapter 9. Now let us see how light refracts through a prism. Refraction of light through a prism. If I draw the front face of the prism, which is triangular, it will look like this. When light, a monochromatic light enters a light of single wavelength or single color, that is monochromatic light, if you allow it to enter, let me mark this as P, Q and R. Then at the surface PQ, if you happen to draw one normal, then it will bend towards the normal, because when light enters from rarer medium to denser medium, then it bends towards the normal. At the surface PR also, if I draw one normal, then you can see that it is traveling now from glass to air, so it will go away from the normal. This ray, the incident ray, let us mark it as AB. The refracted ray BC and the emergent ray CD, let it be. The angle between the incident ray and the normal, we call it as angle of incidence. The angle with the refracted ray and the normal, you will have two angles like this, refracted ray and the normal. One we mark it as R1, the other one we mark it as R2. And the angle between the emergent ray and the normal, we call it this angle of emergence. Now because of this prism, you can see that light is bending twice towards the base of the prism because of its surface, the position of the surface. Now if the prism was not present, then light would have gone this way. It will have traveled this way. But by placing the prism, the emergent ray is traveling this side. If you extend it, you can see by how much it got deviated because of prism. Then you will get this angle, let it be K. This angle between the incident ray and the emergent ray, we call it as angle of deviation. Now here in this refraction of light through a prism, there are some certain relations that you can derive. There are three derivations that you have to know here. The first derivation is that you should be able to prove the angle of the prism. This is your angle of the prism. This one, we write it as A, angle A. Don't get confused with this letter A. The angle of the prism A is always, if you add with angle of deviation, you always get angle of incidence plus angle of emergence. Angle of the prism plus The angle of deviation is equal to angle of incidence plus angle of emergence. Let us prove and see. To start the proof, you can do like this. First find this angle, angle KBC. Angle KBC, we are taking in triangle KBC. In triangle KBC, angle KBC will be equal to, this is angle of incidence because vertically opposite angles are equal. So I minus R1. So angle KBC is equal to angle I minus R1. Likewise, you can find this angle KCB. Angle KCB is equal to E minus R2. Here this is angle E, vertically opposite angle, they are equal, minus R2. Now in the same triangle, this del, the angle of deviation, is the exterior angle of the triangle, so it will be equal to sum of KBC plus KCB. Del, the angle of deviation is equal to angle KBC plus angle KCB. So this is exterior angle property. Now del is equal to KBC, we found out here, I minus R1, plus angle KCB is E minus R2. So this is I plus E, take together. The minus term we take common, R1 plus R2. So like this you'll get the angle of deviation. Let it be equation number 1. Now if you look at the formula, A, I, E, A is missing, I, E and angle of deviation, they are present. This one will be replaced with A. That we'll have to find out now. In triangle BOC, angle R1 plus angle R2 plus angle BOC is equal to 180 degree. The angle sum property. The sum of three angles in a triangle is 180. Now, if you look at this quadrilateral PBOC, in quadrilateral PBOC, these two angles, angle PBO is 90 degree because this is normal to the surface, and angle PCO is also 90 degree, normal to the surface. So sum of these two angles is 180. Angle PBO plus angle PCO together is 180. So the remaining two angles, angle A and angle O, these two sum also must be 180 because in a quadrilateral the sum of all the four angles measures 360 degree. Therefore, angle A plus angle BOC is also 180. Let us mark this as equation number 2 and this one as equation number 3. Now if you compare equation 2 with 3, you will find that angle A is equal to R1 plus R2 because right hand sides are equal, so left hand sides also must be equal, and these two angles are equal. As they are equal, they will get cancelled. So what we can get is R1 plus R2 is equal to A. Let us mark this as equation number 4. Now if you put the value of R1 plus R2 in equation number 1, put in R1 plus R2, value of R1 plus R2 in equation 1, we get angle of deviation is equal to I plus E minus, it was R1 plus R2, that will put it as A. So del plus A or A plus del is equal to I plus E. Like this you can get the relation. Let us mark this as equation number 5. Now the second proof is that to prove for a small angled prism, if the angle of the prism is very small, for a small angled prism somewhat like this, with angle around say 5 degree, or a thin prism, or 15 degree or 20 degree, then there is a different relation. The relation is that angle of deviation is equal to refractive index of the prism minus 1 into angle of the prism. Let us prove and see. In this proof, you will use Snell's law at these 2 points B and C. When light passes from air to glass, at the interface, PQ, sin I by sin R1 is equal to refractive index of glass with respect to air. This is by using Snell's law. You can get like this. For small angles, sin theta and tan theta is nearly equal to theta. For small angles, sin theta is nearly equal to theta. Therefore, sin I can write it as I by R1 is equal to refractive index of second medium with respect to first, or I is equal to R1 refractive index of second medium with respect to first. Let me mark it as equation number 1. So I'll take it as equation number 1. Now at the interface PR, again by using Snell's law, sin R2 by sin E, sin R2 by sin E will be refractive index of first medium with respect to second. Here also for small angles, sin R2 we can write it as R2 divided by E is equal to refractive index of first medium with respect to second. But if we do refractive index of first medium with respect to second, then it will come the reverse way. We are going to find out the refractive index of glass. So we'll make it refractive index of second medium with respect to first, and this will be E divided by R2. Reciprocate it both the sides. So from here you will get E is equal to R2 refractive index of second medium with respect to first. Let us mark this as equation number 2. Now putting the values of I and E, in the equation, our equation A plus del is equal to I plus E. There we will put it. If you put it here, you will get like this: A plus del equal to I. It is R1 refractive index of the prism plus E is here, R2 refractive index of the prism. Now, refractive index of the prism, if you take common, then you will get here R1 plus R2. It's A plus del. Now, if R1 plus R2, we know that it is equal to the angle of the prism into the refractive index of the prism. That is equal to A refractive index of the prism minus angle of the prism. Refractive index of the prism minus 1 if you take A common. So like this you can find out the angle of deviation for a small angle prism. Now let us say about prism formula. The earlier two derivations that we have done is not called prism formula. It is a relationship that exists between the angles. Now, the prism formula is this one. Refractive index of the prism is equal to sine A plus angle of minimum deviation divided by 2 sine A by 2. Here A is the angle of the prism, not this A. If you get confused, change this one as something like X or something other than that, other letter you can use. Now to prove this prism formula, you'll have to know about this angle of minimum deviation. Let us discuss first what is angle of minimum deviation. If you go on increasing the angle of incidence, then the angle of deviation at first goes on decreasing. But still further, if you go on increasing the angle of incidence, then the angle of deviation, you will take a U-turn, it will go on increasing again. So the minimum value of this deviation, we call it as angle of deviation. It will look somewhat like this. Suppose this angle of incidence and this angle of deviation. For smaller angles, 30, 35, 40, 45 degree, 50 degree, 55 degree and so on. If you go on increasing the angle of incidence, here at first it will show decreasing, it will come decreasing, 60, 54, then it will become 40, then it will become 38 suppose, then it will go on increasing again 40, 54, like that it will go on decreasing first, and after that will start to show increment. First it will decrease, it will reach a minimum value, after that it will become more and more. This minimum angle, we call it as angle of minimum deviation. The least deviation produced by a prism is called the angle of minimum deviation. If you plot it in a graph, it will look like this. If I take along x-axis angle of incidence and along y-axis if I take angle of deviation, then it will come down like this. In angle of incidence, if it goes on increasing, at first the angle of deviation will become lesser and lesser. It will reach a minimum value, and further if you go on increasing the angle of incidence, again the angle of deviation will become more and more. So this angle at a particular angle of incidence, this angle of deviation will be called as angle of minimum deviation. There can be two values of angle of incidence for which the angle of deviation is same. There can be two values of angle of incidence for which the angle of deviation will be equal. So the graph looks like this. Now at this minimum deviation position, you get the prism formula. Now let us derive and see. In minimum deviation position, what is minimum deviation position? Then you should be able to say that the Prism is said to be in minimum deviation position when the angle of deviation is minimum. The name itself says minimum. So in this minimum deviation position, the angle of deviation we replace with angle of minimum deviation, del m we write. Then angle I is exactly equal to angle E in minimum deviation position. These two angles will be exactly equal, and R1 is also equal to R2, the two refracting angles. R1 is equal to R2. Let us take it as R, say. If there is only one R, both equal to R, then better say that it is R, the angle of refraction. So we can get the expression like this. You'll get it. We know that angle A is equal to R1 plus R2. Earlier we have seen R1 plus R2 is equal to angle A, the angle of the prism. A is equal to R plus R. Now we are taking both R1 and R2 equal to R. A is equal to 2R. So R is equal to A by 2. Find out R first. Like this, also we know that A plus del is equal to I plus E. So A plus del, now del is minimum deviation, so we write del m. I plus I can write because I is equal to E here. So it will give you 2I. So I will be A plus del m divided by 2. So I is equal to A plus del m divided by 2. After finding out I and R, you will use Snell's law and get this relation. Using Snell's law, refractive index is equal to, this is for the material of the prism we are taking, mu2 with respect to 1, sin I by sin R. Sin I is A plus del m divided by 2, and sin R we got angle of the prism A divided by 2. So this way you can derive the prism formula. Here I is A plus del m by 2 and R is A by 2. You have to keep in mind that this is angle of incidence of the prism in minimum deviation position, and this is angle of refraction A by 2. Now let us do some numericals and make that concept more clearer. Let us solve these two questions based on your formulas you got in prism. A thin prism of 5-degree angle. The angle of the prism, we are doing number 1. Solution number 1. The angle is only 5 degrees, so angle of the prism A is equal to 5 degrees. So it is a thin angle prism. Gives a deviation of 3.2 degrees. Angle of deviation is 3.2 degrees. What is the value of refractive index? That means you are asked to find out the refractive index of the prism, mu, of the material of the prism. This one we are going to calculate. Now, as we know that for a thin prism, angle of deviation is equal to mu minus 1 into angle of the prism. This is a relation we know for a small angle prism. Del, the deviation angle is 3.2 degrees. Refractive index we are going to find out, and angle of the prism is 5 degree. So if you cross multiply 3.2 degree divided by 5 degree is equal to mu minus 1. Now degree it will get cancelled. 5 6 are 30. Decimal will come here. 5 6 are 30, and then 2 0 5 4s are 20. It's equal to mu minus 1. So mu will be 0.64 minus 1 will become plus 1. Mu is equal to, the refractive index is equal to 0.64 plus 1. So you will get 1.64. Like this you can find out the refractive index of the material of the prism. This is the first solution. Now let us see the second one. In the second question, a ray of light suffers minimum deviation while passing through a prism of refractive index 1.5. Refractive index is 1.5. It suffers minimum deviation. Keep in mind the conditions when minimum deviation occurs. And refracting angle 30 degree. So if the refracting angle is 30 degree, then we know that A plus A is equal to R1 plus R2. Here it will be R plus R. A is equal to 30 plus 30, we will get it 60 degree. So the angle of the prism is 60 degree. So you have to know this. Then refracting angle is given. Calculate the angle of deviation. You are asked to find out the angle of deviation, that is minimum deviation, del m. They are asking you to find out. And angle of incidence also. Angle of incidence you can find out from the relation. Your relation is mu is equal to sine A plus del m by 2 divided by sine A by 2. So your angle of deviation, angle of incidence will be this one, because this relation we got it through sin I and sin R. This I value is A plus del m by 2. Using that relation we can find out the angle of incidence. Now let us write down the formula. We know that refractive index is equal to sin A plus del m divided by 2 sin A by 2. After writing the formula, we put the values. This will give us 1.5 is equal to sine, angle of incidence is 60 degree, angle of the prism is 60 degree, plus angle of minimum deviation divided by 2, the whole thing divided by sine 60 degree divided by 2. So the next step, 1.5 is equal to sine 60 plus del m divided by 2. Here you will get sine 30 degree. 60 by 2 is 30 degree. Sine 30 degree, you know the value, how much it is? 60 degree plus del m divided by 2. Sine 30 degree is 0.5, is 1 by 2. 1 by 2, if you divide, you get 0.5. Cross multiply this term, the unknown term will bring here. Sine 60 degree plus del m by 2 is equal to 0.5 into 15. 15 5s are 75. So you will get 0.75. You will get 0.75. So to find out 60 degree plus del m by 2, you will do sine inverse. Sine inverse of 0.75. And it will be given to you in the question. If you are writing board exam, it will be given on the front page of the question paper. So you have to check it. Sine inverse of 0.75 equal to 48.6 degree. 48.6 degree. Now you can cross multiply. If you cross multiply, you will get 60 plus del m is equal to 48.6 into 2. You multiply 2 6 are 12, 2 1 in hand, 8 2 are 16 plus 1 17, 7 1 in hand, 8 plus 1 is 9. The decimal is after 2 digit. So angle of minimum deviation will be 97.2 degree. This is degree minus 60 degree. So it is 37.2 degree in our calculation with the given incidence. To find the angle of I, you have your formula A plus del m divided by 2. Now angle of the prism is 60 degree plus angle of minimum deviation you got 37.2 degrees divided by 2. So add it 97 0.2 degree divided by 2. 2 4s are 8, 2 8s are 16, 2 6 are 12. Like this you can find out the angle of dispersion of light by a prism. You all know that when white light passes through a prism, then it gets split up into its 7 constituent colors. If I allow white light to pass through a prism, then this is white light. White light is that light which contains all the 7 colors like our sunlight. If you allow it to pass through a prism, instead of going straight like this, it will bend slightly like this towards the base of the prism. And the other colors, this is the red color will be at the top. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and this is the last one, that is 7. So these 7 colors, they will get dispersed. So when we say dispersed, dispersion is the phenomena due to which a white light gets split up into its 7 constituent colors. Now this phenomena, we call it as dispersion of light, and the band of 7 colors thus formed is called spectrum. The 7 colors that you can see that is emerging out of the prism if you keep one screen here, you can see that the bottommost will be your violet, VI, VG, YO and R. These are the 7 colors you see on the screen. This is your screen. And if you look very carefully, you will find that the red color is deviating the least and the violet light is deviating the maximum. Now let us see the cause of dispersion. Why they are dispersing? Cause of dispersion to understand. Let us take Cauchy's expression. He gave us the relation between the refractive index and the wavelength. It goes like this and so on. Now from here what we can understand is refractive index is inversely proportional to the wavelength. Now since wavelength of violet light is less than the wavelength of red light, refractive index of violet light will be more than refractive index of red light. Also we know that for a thin prism, angle of deviation is equal to refractive index minus 1 into angle of the prism. From here, we understand that angle of deviation is directly proportional to the refractive index mu. So if violet light refractive index is more, the deviation also will be more. So therefore, we can write deviation of violet light is more than deviation of red light. You can see here the deviation of violet light is more than the deviation of red light. Now let us see some terms related to dispersion of light. There are 2 terms you have to know. The first one is that angular dispersion. Angular dispersion, we write it as theta. It is defined as Angular dispersion is defined as the difference between the two deviations. One is for violet light, the deviation is more, and for red light, the deviation is less. So the angle of deviation of violet light and red light, the difference, we call it as angular dispersion. Okay, if you look at the diagram, this violet light, if I produce it, I'll get here angle of deviation for violet light. And if I produce this red light, then the angle is less. Then you can get the angle of deviation for red light. So this difference of these two, we call it as angular dispersion. Here, deviation produced by violet light, you can give it as mu v minus 1 into angle of the prism, minus del r will be mu r minus 1 into angle of the prism. So if you open the bracket, you will get like this. Minus into minus is plus a. Plus a minus a, if you cancel it, you will get mu v a minus mu r a. And if you take a common, then you will get a relation for angular dispersion. There are two factors on which angular dispersion depends. The first factor is that it depends upon the angle of the prism. It depends upon the angle of the prism, and it also depends upon the refractive index of the prism. Refractive index of the prism, of which material it is made up of, or you can say that it depends upon the material of the prism. Like that also you can say. The next term that you'll have to know is about dispersive power. The second one, dispersive power, we denote it with this omega symbol, or we call it as dispersive power. Dispersive power is nothing but it's a relation or a ratio between this angular dispersion produced by a prism divided by the mean dispersion produced by all the light, VIBGYO R. Mean dispersion, we simply write it as del. So angular dispersion or dispersive power, it is the ratio between theta and the mean dispersion produced by the prism. And as you know, theta is equal to mu v minus mu r into angle of the prism, and dispersive power is mu minus 1 into a. You can cancel these two and get the relation for dispersive power. Omega is equal to mu v minus mu r divided by mu minus 1. And dispersive power depends upon only the nature of the material of the prism, or we can say that it depends upon the refractive index of the prism. It depends upon only one factor. It does not depend upon the angle of the prism. As you can see here, the angle got cancelled. Now let us see the natural phenomena due to sunlight in dispersion. Sunlight, as we know, it produces a rainbow whenever there is water particles or droplets of water in the atmosphere. The two essential conditions to see the formation of rainbow is that, first of all, one part of the sky, if it is shining, then the other part there should be droplets of water. Hence on the opposite side there should be droplets of water. That is one condition. The second condition is the observer should keep his back towards the sun. We'll have to keep the back towards the sun. Then the rainbow will be formed on the other end. These are the two essential conditions to see rainbow. Rainbows are also classified into two types. One is called your primary rainbow. In primary rainbow, the violet light will be at the bottom, exactly like your prism, and red will be at the top. Whereas in secondary rainbow, the red light will be at the bottom and the violet light will be at the top. So that rainbow we will call it as secondary rainbow. But let us see now first how primary rainbow is formed. Suppose this is a droplet of water, and if ray of light comes, it is a three-step process. Sunlight, if it comes and strikes, first here it will undergo refraction. After undergoing refraction, here it will undergo total internal reflection, and while undergoing this refraction, actually it is splitting up. Slightly it is splitting up, here also splitting up, and then it is coming out. But when we draw a single ray inside the water droplet, and then here we can draw like this, the two ends of the rainbow. A person looking from here, this way you can see, here the angle must be 40 degree and here the angle must be 42 degrees. Then he can see the rainbow. This is how it is formed. This is a three-step process. Again I repeat, here one refraction will take place, then here total internal reflection at this point is reflecting back, and at this point again refraction takes place. Then you can see this primary rainbow. Now let us see about secondary rainbow, the second one. Secondary rainbow. In secondary rainbow, this is very rare. Sometimes if you are very lucky, you can see the red light at the bottom and violet light will be at the top. It is a four-step process. Secondary rainbow is a four-step process. Suppose this is a water droplet and the ray of light is coming this way, refracted, then undergoes total internal reflection one time here. Again here undergoes total internal reflection, that means two total internal reflection, and ultimately it refracts and comes out. So in this case, the observer looking at this rainbow, this angle will be around 50 degree, and at this point it will be around 53 degree. Then he can see the rainbow. You are observing from here, the observer is observing from here. So in this case, here one refraction, here total internal reflection, again here total internal reflection, and at this point again refraction, then it emerges out from the water droplet. This is how primary rainbow and secondary rainbows are formed. Thank you and have a nice day. Stay tuned with LFI Educate.